Hello, yes, and welcome to Notes 5.3, where we're going to draw the connections between matrices and systems of equations. So the cool part here is that you can actually use matrices to represent systems of equations, and one way we do that is through an augmented matrix. An augmented matrix is a matrix that represents the coefficients and constants of a system of equations. So, looking here at letter 1, negative 5x plus 2y equals 10, 3x plus 1 equals 0, we can write that as a matrix where it would be a 2 by 3 matrix, negative 5, 2, 10, 3, no y, and notice we have this equal sign here, so I would have to rewrite this as 3x plus 0y equals, that means I would have to move that over, negative 1. So negative 1. So it's important that when we write these, we write them in a standard form. So this first column here represents my x's, my y's. Imagine an equal sign here, and sometimes you'll actually see a dashed line like that, and then my constants, all right? And you can use that dashed line, that's totally fine. So looking at number 2, what if there are 3 equations with 3 variables? Well, we'd have x, which is, its coefficient is 1, y, negative 3, 2z is 6. There's no x, so we'd put a 0 there. 1y, negative 1z, and 10. Negative 1x. What is happening here? I do not know. That's new. Okay, that's still occurring. All right, negative 1x, 3y, there's no z's, and 5 would be my constant there. Again, imagine that dashed line there separating the variables from the constants. All right, now this one, we have it rearranged a bit. If you want, you can write it in order. So it'd be x plus 2y is 4, 7x minus y equals 10. You always need that x, y constants if there's 2 equations. So this would become 1, 2, 4, 7, negative 1, 10. There we go. And number 4. Oh, all sorts of order going on here. Let's write this out in a correct order first. So we'd have x plus 2y. I'd need to subtract z. That's negative 1. Subtract the 2x, so negative 2x minus y plus 3z is 8. And then this one's just out of order, so negative 4x plus 3y plus z will equal 6. So as a matrix, what would that look like? Well, 1, 2, negative 1, negative 1, negative 2, negative 1, 3, 8, negative 4, 3, 1, 6. There we go. So these matrices are used to represent systems of equations. So now that we've gone from systems to augmented matrix, let's go augmented matrix to systems. So looking at number 5 here, this would be saying we always assume this column is x, y, coefficients, or constants, excuse me. These are the coefficients. Negative 7, 1, 0, 1. Those would be the coefficients for x, coefficients for y, constants. So that being said, this would be negative 7x equals 6, and x plus y equals 10. Now if it's a 3 by 4, we assume that this first column is x, this is y, z, and the constant. So we would have 5x plus 2y plus 6z equals 3. 3x minus 4z is 9. And let's see, x plus y plus 3z equals negative 4. There we go. All right, number 7 here, we would have negative x plus y is 8. 3x minus 4y is 6. Okay, 3 by 4, so x, y, and z, and then the constants are that last column, so we'd have negative x plus 2y is 6, y plus 3z is 8, and 5x minus 4z equals 3. So augmented matrices are one way that we can represent systems of equations as a matrix. Another is a matrix equation. Now, the key difference between these is that a matrix equation is an equation, and therefore it has an equal sign. It's composed of multiple matrices. So matrix equations are an equation of matrices that identifies the coefficients variables and constants of a system. So with that being said, the first matrix tells us our coefficients, the second one tells us our variables, and the last one tells us our constants. So this first one would be 4x plus 2y equals 5, negative x plus y equals 3. So this first matrix represents our coefficients. Like I said, coefficients here, variables here, constants here. So looking at this one, we have 3 equations, 3 variables, 3 constants. So negative 2x plus z equals 1, 3x plus 5y plus 2z equals 2, negative 4x minus 3y plus 6z equals 6. Why don't you go ahead and try 3 and 4 on your own? Go ahead and pause it. Try 3 and 4 on your own. I'll give you a little bit of time. Pause the video and then we'll check it together. All right, let's see how he did. So number 3 here would be x plus 2y equals 3, and 3x minus 4y equals 1. 4 would be x plus 2y plus 5z equals negative 1. Y plus 3z equals 5. 3x minus 4y equals 7. There we go. All right, so now that you've seen that, why don't you try to flip it? Go ahead and try number 5 and 6 on your own here. Take it from a system into a matrix equation. Go ahead and pause the video and try that. All right, let's see how we did. So first matrix is my coefficients, so 3, 2, negative 4, negative 3. Next is my variables, x, y. Notice it's always just one column, and it equals my constants, 1 and 0. Excellent. Number 6, 3 by 3 for this first one, so I have 1, 0, 1, 3, negative 1, 2, 0, negative 1, negative 4. My variables were x, y, and z, and they will equal 2, 5, and 3. There you go. All right, so hopefully we're feeling pretty good about those. The one more thing that we're going to talk about before we get into really solving systems with matrices is row operations, which is a process that the addition, subtraction, multiplication, words are hard, of rows within an augmented matrix. So it's basically using operations within a matrix to manipulate the rows. So how it looks is given a matrix. So for example, we have this 3 by 2 matrix here. We're going to change row 3. That's what we're going to change in this matrix. So negative 5, 4, we're going to replace it with 1/2 of R1 plus R3. So what does that mean? First of all, it means that we're going to rewrite this matrix A with a new row 3. So only row 3 is going to change. So that means the first two rows are not. 2, negative 1, 3, 2. Now, instead of writing negative 5, 4, we're going to add 1/2 of R1 to R3. So 1/2 of R1, 2 and negative 1. This is row 1. This is row 3. All right. So 2, 1/2 of 2 is 1. 1 plus negative 5, which is that first column of row 3. So 1 plus negative 5 would become negative 4. 1/2 of R1, negative 1. So that would be negative 1/2 plus 4 would be 3.5, although we don't use decimals in matrices. So we would write this as a fraction 7/2. That kind of looks like a z, though. Let's try that again. 7/2. And there we go. That's what that would look like. So let's try another one. Row 2, which is the second row here, that's our 2. D2, of course. Row 2 equals 2 times R3 minus R2. So which row is going to change? Row 2. So let's go ahead and write row 1 and row 3 with the original one. So 2 and negative 1 and negative 5, 4. Okay, now instead of 3, we're going to have 2 times R3, 2 times negative 5, so negative 10, minus R2, negative 3. So negative 10 minus 3 is negative 13. 2 times R3 is 4. 8 minus R2 is 2. 8 minus 2 is 6. So there's an example of addition, there's an example of subtraction, and then we can also just do multiplication, where we're going to replace R3, that's what we're going to change. So row 1 and 2 stay the same, 2, negative 1, 3, 2, and it's going to be replaced with 2/3 of R1. So this would be 2 times 2/3, which is 4/3. 2/3 times negative 1 will just become negative 2/3. And there we go. So that's an example of row operations. What they'll often have you do on the test, and again, I won't be able to see this test, I have no idea what it will look like, is they'll give you a matrix to start with, and then for each subsequent part, we use the result of the previous. So we'll start with this matrix A, we'll do number 4, and then based off number 4, we'll do number 5, and based off number 5, we'll do number 6. So let's try that one together. So R3 equals 5R2 plus R3. So what does that tell me? Only R3 is going to change. So that means the rest of the matrix is going to stay the same. Negative 1, negative 2, 3, negative 2, 2, negative 5, 1, negative 7. Now instead of R3, I'm going to do 5 times R2 plus R3. One way that you can do this is create a little system here that you're going to add, which is what I kind of like to do if there's a bunch of numbers going on here. So 5 times R2. So I'm going to start by multiplying the second row times 5. So I'm going to get 10, negative 25, 5, negative 35. And below that, I'm going to write R3. So 5, 4, negative 7, 6. And then I'm just going to add these numbers together. So 10 plus 5 is 15. Negative 25 plus 4 is negative 21. 5 plus negative 7 is negative 2. Negative 35 plus 6 is negative 29. This then becomes my new R3. So 15, negative 21, negative 2, negative 29. So I'm going to use this row, this new matrix that we've created with number 4, for number 5 now. All right. So I'm going to change R1 to be negative 4R2 plus R1. So which row is going to change? Well, R1. So that means rows 2 and 3 stay the same. 2, negative 5, 1, negative 7, 15, negative 21, negative 2, negative 29. All right. Now row 1 is going to become negative 4 times R2 plus R1. So let's do negative 4 times R2. So R2 is 2, negative 5, 1, negative 7. So multiply all those numbers times negative 4. So I'll get negative 8, 20, negative 4, and 28. And we're going to add that to R1, which was negative 1, negative 2, 3, and negative 2. Let's add all this together. So negative 8 plus negative 1, what's that going to be? Negative 9. 20 plus negative 2 is 18. Negative 4 plus 3 is negative 1. 28 plus negative 2 is just positive 26. So that row is going to become my new R1. Negative 9, 18, negative 1, and 26. And lastly, it says R1 is going to be multiplied by 1/7. So I can just put everything in R1 over 7. So I'm going to have negative 9 over 7, 18 over 7. Again, no decimals, always fractions in a matrix. And then R2 and R3 stay the same. 2, negative 5, 1, negative 7, 15, negative 21, negative 2, negative 29. There we go. And those are row operations. And the reason that row operations become a thing in matrices is because it's elimination of the system of equations, right? Think about when you do elimination, you multiply an equation times a constant and then add it to the other equation to eliminate a variable. That's what we can do. However, instead of us doing it by hand, the calculator can totally do that for us. And that's when row echelon form comes in. Row echelon form is an augmented matrix that can be solved backwards. Now, one of the things about row echelon form and one of these things about augmented matrices, if they represent a system of equation that's solvable, there must be one more column than rows. Think about all the matrices that we've dealt with so far. There's one more column than rows. That one didn't. But if we look up here, you know, we had 2 by 3s or 3 by 4s. That needs to be the case because that means there's the same number of equations as there is variables. So to get something into row echelon form, let's go ahead and do this first example together and we'll walk through it up here. So the first thing is press second and matrix. And that's going to show us the name of those matrices. So second matrix. Click over to edit and select the matrix we want to edit. We can use matrix A, that's fine. We're going to input the order of the matrix. So since we're doing number 1 here, this is a 3 by 4. So 3 by, see I messed up already. Second matrix, go over to edit A, 3 by 4. All right, now I got space. So I'm going to type in the value, so negative 6, 2, 1, 4, 0, 3, 2, negative 5, 1, negative 1, 0, and 7. All right, once we're finished, click second and quit. Done with that. All right, so now we're going to talk about how to solve it. So we're going to press second and matrix, and then we're going to click over to math. Second, matrix, click over to math. From there, we're going to scroll down quite a ways, actually. We're going to scroll all the way down to AREF. And that literally stands for row echelon form, REF, row echelon form. So we're going to press enter once we found that. And notice now it's saying REF of what? this is where we need to put our matrix. So we'll click second matrix. We'll select the matrix we edited, which was A, press enter. We're going to close the parentheses and press enter. Our matrix should now be in row echelon form. So let's see. Interesting. Okay, so we get decimals. We don't want decimals, so we can always hit math and press enter. That'll make them all fractions. And here we go. All right. So I said something is in row echelon form when it can be solved backwards. Here's a couple other traits we can be looking for. Notice this main diagonal, that diagonal that goes from top left to bottom right. That main diagonal is all ones. Anything below those ones are 0. That tells you we're in row echelon form. What I mean by solve backwards is this, remember, represents a system of equations, so x, y, and z. So this tells me that z equals 118 over 11. I can then plug that in up to this equation and get a value here, and I can then solve that for y. Once I have y, I can plug it in up here, plug in z up here, and then I can solve for x. That's a lot of algebra still, but it's what we can use to solve. So let's go ahead and copy this down in row echelon form. So we're going to have 1, negative 1/3, negative 1/6, and negative 2/3. 0, 1, 2/3, and negative 5/3. And 0, 0, 1, and 118 over 11. Gross. Don't worry, you probably won't be solving anything that actually looks like that. That's pretty gross. All right, let's try one more together. So second matrix, we're going to do number 2 here. So let's edit matrix A to turn it into a 2 by 3, 2 rows, 3 columns. 4, 1, 3, negative 2, 5, and 8. Press enter. Excellent. Second, quit. So I'm going to go second matrix over to math. Go all the way down to letter A, R, E, F. Press enter. Second matrix. A is what I edited, so I'll press enter, close the parentheses. And here we go. Don't like that. Turn it into fractions. Math, frac. Beautiful. All right. So this one was 1, 1/4, 3/4, 0, 1, 19/11. All right, why don't you try one on your own? Go ahead and pause the video, try number 3 on your own, and then we'll check it together. All right, let's see how we did. So I'm going to go second matrix. I need to input this matrix, so I'm going to edit matrix A. This is a 3 by 4. Be sure we get that order in correctly. So 1, negative 2, 5, 3, 0, 7, negative 1, 4, 8, 2, 0, and negative 3. Excellent. So second, quit. Second matrix, over to math, down to REF. Second matrix, I want to reduce A and press enter. Here we go. Let's math, frac. Beautiful. All right. Yeah, I remember this one. Excellent. So I'm going to need some space to write all this. So 1, 1/4, 0, negative 3/8, 0, 1, negative 1/7, and 4/7, 0, 0, 1, and 261 over 262. And close it up like that. Beautiful. All right, so you could use row operations where we add and subtract and eliminate values, right? We use that elimination process to get it to look like this that you can then solve backwards. Once I know z, plug it in for the next equation, figure out y, plug it in for the top equation, figure out x. Or there's another way which is much easier because that just sounds exhausting, all right? And to do that is reduce row echelon form. So row echelon form was an augmented matrix that could be solved backwards. Reduced row echelon form is an augmented matrix that identifies the value of each variable. Value of each variable. Gorgeous. All right, and to get that, it's very easy. You do the exact same process, only instead of second matrix, over to math and down to REF. You go one more, RREF, reduced row echelon form. So instead of REF, we're pressing BRREF. All right, so that's how you do it with your calculator, but you still have to show some work, okay? So I want to show you that process. So when solving systems of equations, first thing is write the augmented matrix representing the system. Augmented matrix. Next thing, use the RREF process to reduce. We're going to write that matrix in reduced row echelon form. And then lastly, we're going to write our answers as coordinate pairs. Remember, because they represent systems of equations, which means this is the point where these lines all intersect, either in two-dimensional space with number 1 or in three-dimensional space with number 2. All right, so let's do 1 and 2 together, and then I'll have you do 3 and 4 on your own. So looking at number 1, first step, write the augmented matrix. So this would be 3, 2, 1, -4, -3, 0. Next, I draw an arrow, and above that arrow, I write RREF, because this is where I'm going to write my reduced row echelon form matrix, and this is explaining how I got from this matrix to this new one that I'm going to have here. So let's go ahead and do that. So we need to edit matrix A. It's going to be a 2 by 3. We have 3, 2, 1, blast off. We have -4, -3, and 0. Excellent. So second quit. Second, matrix. Math. Go down, down, down in an earlier round. Sugar, we're going down. B, reduced row echelon form. Second, matrix. Input that matrix we just edited. Enter. Notice what happens here. You know you're in reduced row echelon form when you have 1s on the main diagonal, 0 for all the other coefficients, and the constants. So think about what this is saying. Let's write this out. 1, 0, 3, 0, 1, -4. This is saying x plus 0 equals 3, y 0 plus y equals -4. So they're saying x equals 3, y equals -4, which is the coordinate point 3, -4. There we go. Now we're in three-dimensional space, so we have 3 variables, x, y, z. That's the exact same process. We'll write our final answer as x, y, z. So this is all the work we need to show for number 1. Let's make sure we have all this work when we're in three-dimensional space for number 2. So first step, augmented matrix. So 2, 1, 3, 1, 2, 6, 8, 3, 6, 8, 18, 5. Let's type that into our calculator. So I'm going to second matrix, edit matrix A, turn it into a 3 by 4. So I need 2, 1, 3, 1, 2, 6, 8, 3, 6, 8, 18, 5. Second quit, second matrix, over to math, Go downtown in an earlier round. Reduce row echelon form. Second matrix. Oh, I need just the matrix A that we edited. Close the parentheses. Beautiful. Now we do like fractions, so I can math frac. I saw some decimals in there. So I'm going to write this out now. So it'll be 1, 0, 0, 3/10, 0, 1, 0, 2/5, 0, 0, 1, 0. So x is 3/10, y is 2/5, z is 0. So my final answer here will be 3/10, 2/5, 0. There we go. Beautiful. That's excellent. All right, why don't you try 3 and 4 on your own? Go ahead and give it a shot. Pause the video, try 3 and 4 on your own. See if we can't solve these systems represented or using matrices. All right, let's see how we did. So looking at 3, I'm going to start by writing the augmented matrix. So 4, -7, 18, -1, 4, -9, RREF. So second matrix, go over to edit this 2 by 3, 4, -7, 18, -1, 4, -9. Second quit, second matrix, go over to math, scroll down, RREF, second matrix, I edited matrix A, put it in there, 1, 0, 1, 0, 1, -2. So I'll have 1, 0, 1, 0, 1, -2, which tells me that x is 1, y is -2. Hopefully we found that for number 3. Let's try number 4 now. So I got 3, -3, -1, -5, 2, -1, -4, -18, -6, -1, 4, and 6. All right, RREF. Let's figure out what we got here. So second matrix, edit this one so that it becomes a 3 by 4. 3, -3, -1, -5, 2, -1, -4, -18, -6, -1, 4, and 6. Beautiful. Second quit. Second matrix. I'm going to use RREF. There we go. For matrix A, close my parentheses, press enter. All right, not bad. So 1, 0, 0, 2, 0, 1, 0, 2, 0, 0, 1, 5. So this is telling me x is 2, y is 2, z is 5. 2, 2, 5 would be the solution for that three-dimensional system of equations. So in all of these matrices, we had one solution. The lines intersected at one point. But we know that's not the only option. If we remember from 5.3, there's two other options: infinite solutions or no solutions. So remember that matrices represent a system of equations. So what I'd like you to do is go ahead, pause the video, and graph these two systems, number 1 and number 2. Go ahead and graph them on this coordinate plane provided, and then we will move forward after you do that. All right, hopefully we got these graphed. They look like this. On number 1, I can see that the lines never touch. So in that case, that means that there is, popping off here. In that case, that means that there are no solutions, right? Those lines are never going to touch. On number 2, the two equations represent the same line, which means that in that case there are infinite solutions. So we need to know how to detect that if we're solving using a matrix. All right? To determine if a matrix has infinite or no solutions, step 1, solve the matrix using RREF. If the matrix has no solutions, all right, if it has no solutions, the bottom row will read all 0 coefficients and a non-zero constant. So what I mean by that, the bottom row will be something like 0, 0, 0, 1, assuming this had 3 variables. They're saying 0x plus 0y plus 0z equals 1. This is the same thing as saying 0 equals 1. We can tie that back to when we solved using substitution and elimination in 5.1. If we got that as our equation, we knew that there was no solutions. Now, if the matrix has infinite solutions, the bottom row will read all zeros. Everything will be 0. So it'll just be 0, 0, 0, 0, aka 0 equals 0, which is true, which is meaning that no matter what the values of the variables, we're going to get that. Now again, it's the bottom row, it's the last line of the matrix. That's what you look for, okay? So with that being said, let's try a couple of these on our own, see if there are infinite solutions, no solution, maybe there's one solution. Let's find out. So looking at letter A, we're still going to show that whole process. So the first step is an augmented matrix. So 3, 4, negative 1, 27, negative 9, 5, oh, see, this is where they almost get you. There was no y, 5z, negative 17, 6, negative 4, negative 4, negative 10, and we are going to RREF this matrix. So let's put it into our graphing calculator. So second matrix, I'm going to edit matrix A, which is already a 3 by 4, which is nice, and we have 3, 4, negative 1, 27, negative 9, 0, 5, negative 17. Did that say negative 18? Did I type that wrong? So you gotta be extra cautious when you do this. Yeah, it's negative 17. Very good. All right, because this is your work, right? So you have to be really careful. So 6, negative 4, and negative 10. Excellent. So second matrix, go over to math. If you go up, that's one way to get there a little faster, to get to RREF. Select matrix A, press enter. Here we go. All right, math, frac. Let's see what we get here. Look at this bottom row. All zeros. Okay, we need to write this matrix down. We definitely need to write this matrix down. So it's going to be 1, 0, negative 5 ninths, 17 ninths, 0, 1, 1/6, and 16 thirds. But that bottom row, all 0. If it's all 0 on the bottom row, what does that tell me? Infinite solutions. Boom, done. Excellent. Infinite solutions for letter A. Let's try another one together. Let's try letter B. Let's put this in RRE, or in augmented form. So we'll have 2, 4, negative 2, 18, 2, 1, negative 1, 11, 5, negative 5, there's no z, and negative 25. And then when we RREF this guy, what are we going to get? So let's second matrix. Over to edit, 3 by 4, 2, 4, negative 2, 18, 2, 1, negative 1, 11, and 5, negative 5, 0, negative 25. Second matrix, math, RREF. Second matrix, A is the one that I edited. Oh, let's math frac this guy again. What do we have here? Oh, look at this bottom row, 0, 0, 0, 1. Well, let's write this reduced row echelon form. So 1, 0, negative 1/3, 0, 0, 1, negative 1/3, 0, 0, 0, 0, 1. The bottom row tells us 0x plus 0y plus 0z, 0 equals 1. No, it doesn't. No solution. That's how we can tell from that one. All right. There are 3, let's see, C, D, E, and F. There's 4 that I would like you to try. Okay, go ahead and try it on your own. Go ahead and be sure to show your work, and then we will check those together, okay? Try it on your own, show your work, check them together. Here we go. All right, so looking at letter C and D, we should have gotten no solution for letter C. For D, we should have gotten infinite solutions. Again, look at the difference between the bottom row of those RREF matrices, right? The zeros with the 1 and then the all zeros. At E and F, we should have gotten no solution for E, 0, 0, 0, 1 on that bottom row. And F was infinite solutions, all zeros on that bottom row. All right, and that pretty much wraps up what we're going to do today. We're going to build on these ideas a bit more as we continue, but isn't that an awesome way to solve systems using matrices? So we now know of another method. We can use substitution, we can use elimination, we can use graphing, or we can use our graphing calculator and solve these systems with matrices. All right, this is Mr. Carter signing off. I will see y'all next time. Hope y'all are staying happy and healthy. Have a math magical day.